Hi, I am Will Shirtliff. I'm the Global Sales Manager for Vehicle Electrification. I work in Parker Hannifin's Engineered Materials Group and have 20 years of experience with seals, EMI shielding, and thermal interface materials. Today's presentation is going to focus on sealing specifically, but Parker will be conducting future webinars to review some of these other areas, such as thermal interface materials and EMI shielding. Today, I'm going to be presenting with Bwani Tripathi, who is also in Parker Hannifin's Engineered Materials Group. He is the Division Engineering Manager for O-rings and Engineered Seals, and he has over 25 years of experience in the rubber and sealing industry, as well as a PhD in mechanical engineering. A little bit of housekeeping before we get going. Everyone's going to be muted during the presentation. If you have any questions as we're going, you can type them into the Zoom meeting, and we do have engineers on standby that can answer those questions as we go. Often when engineers think of sealing components or think of gaskets, if they think of them at all, they think of them as relatively cheap and relatively easy. And in some ways, there's a truth to that. Seals and gaskets are not expensive when you compare them to the battery, for example, or not expensive when you compare them to an electric motor. But they are expensive when they fail. And one of the reasons seals should never be overlooked is because a failed seal can be one of the most expensive things you can have on a vehicle. It can contribute to performance loss. It can contribute to expensive damage of your component. And it can also contribute to safety issues like thermal events. And for that reason, sealing needs to be front and center in any engineer's focus as they're designing their component. Today, we're going to focus on battery sealing specifically, with batteries being one of the most expensive components on an electric vehicle and having some unique sealing challenges within that system. The traditional approaches to battery sealing focus on, there's a lot of molded seals that are used out there. There is form in place gasket technology that is used, and something called room temperature vulcanization, or RTV technology. These three technologies are used throughout the industry to seal batteries, and all of them have strengths associated with them, but also some challenges, some weaknesses associated with them. And some of those challenges that exist are high load, and high load has a lot of drawbacks to it. So when you try and bring together, this is particularly true with a molded seal or a form in place seal, you're trying to bring together the flange, compress that gasket, and what happens is the flange ends up creeping or deflecting as it attempts to keep that gasket compressed. And this can cause damage to the mating components. It can also create a leak path as that component creeps over time, that then contributes to all the downsides to having a leaky battery. And so there's a need in the industry to have a lower load system that does not cause damage to the mating components. Another benefit that a low load system would have is to enable engineers to reduce the number of fasteners that they have on their batteries. A reduced number of fasteners has a lot of benefits, primarily around cost, where each fastener requires obviously the cost of the fastener itself, but also the cost of drilling the hole, assembling the fastener, having, if it's a plastic component, having a load limiter in there for the plastic component. So being able to reduce the number of fasteners definitely helps in terms of the overall cost of the system. Another challenge with some of the existing technologies, and this is particularly true with RTV and form-in-place gaskets, is the serviceability. If you can imagine, for RTV that functions in a lot of ways like a glue, and form and place gasket that adheres to one side of the flange, there is a difficult cleanup process that any mechanic would have to do. So if you can imagine them having to pull apart that joint that's glued or at least partially adhered to one of the joints, and then have to scrape that clean, fix whatever's going on in your battery, and then reapply that seal, and then attempt to hope they got it all cleaned off and are properly reapplying it, and then hope that that seal can then last the rest of the life of that vehicle. And there's a lot of risk associated with that, and some difficulty on the part of the mechanics side associated with that. So having a seal that is easily serviceable is a big need within this industry. Next, cleanliness is a challenge for both RTV and form and place. Both those technologies require a clean atmosphere at your plant. Process contaminants like oil and particulates can prevent adhesion. And so there's a need for a technology that's robust to cleanliness at the manufacturing level. So that's something that is needed in this industry. Finally, tolerance requirements. Most of these technologies require very tight tolerances from a flatness perspective, from a profile perspective, from a deflection perspective. And this drives additional cost. Anytime you have to over-specify your tolerances, you have additional cost, especially when you're looking at a very large component like a battery that is hard to keep flat over the entire perimeter of that flange. And so there's a need in this industry to have larger robustness, greater robustness to tolerances on the mating components. And so at this time, I'm going to turn it over to Bwani Tripathi, and Bwani's going to talk about some new technologies that Parker Hannifin has developed to help address some of these challenges.
Thank you, Will. I'll be elaborating on this new battery perimeter sealing technology. The major difference, instead of molding the gaskets in the conventional way, this technology is based on extrusion and splicing. It involves extruding an engineered profile to a very high level of precision and then splicing the ends together to make a continuous gasket. This technology is most applicable for larger size gaskets, such as the one we are talking about here, the battery perimeter seal. In fact, extruding profiles is not new, as they have been used in many applications, such as door seals, but the precision of extrusion, typically in very small cross sections, which is required for sealing these components with tight real estate, and a splicing technique that provides a very strong joint is the key to the application of this extrusion technology to battery sealing. Most importantly, this technology also opens up a lot of options for design engineers to optimize the best profile, which would otherwise not be possible in molded gaskets. One good example is through a hollow cross section that can be designed to accommodate very high tolerances, as well as cross-section profiles that have multi-directional lips that can enable sealing in multiple planes. And these gaskets can also be made from many different polymer families, depending on the environment that they're required to seal. So how is this technology differentiated, and what benefits do this technology provide? One of the major benefits, as Will mentioned, is low closure force. Closure force is the force required to compress the gasket to generate the desired sealing forces, which is needed for proper and long-term sealing and durability. If a gasket can function under lower sealing forces, then really one does not need to compress the gasket to very high loads, which in turn makes it easier to assemble for the manufacturer. One means to achieve low closure force is to make the profile hollow. This simple chart on the right is an illustration where by changing certain design parameters, we can reduce compression loads by an order of magnitude or more. Now, why is the closure force or compression load so important? Because reduced forces to seal means less load on the flanges, which in turn means less flange deflection, and in the long run, reduced creep of the components. This enables the option to use possibly less rigid structures. Of course, gasket is not the only reason for designing the structural rigidity of the components. In fact, in most cases, the structural rigidity requirements for sealing is not even considered. Um, Essentially, what hollow extruded gaskets can offer us is the potential to achieve good sealing with lower sealing forces, thus be able to use less rigid structures. If a less rigid structure can be used, it can lead to reduced weight, which in the EV application could potentially mean increased range. Another significant benefit in these gaskets can enable reducing the number of fasteners. On a like structure, fastener spacing may not be the sealing may not be the only driver for fastener spacing and the number of fasteners used, but it is in fact an important parameter. Extruded gaskets being able to function correctly with larger bore spans does open up the option to potentially reduce that number of fasteners. This in turn can have impact on overall system cost and could also have some impact on weight. Another point, the precision of the group dimensions can also be relaxed with these extruded spliced gaskets. In solid gaskets, precise groups are needed to prevent overfilling, but in case of these hollow extruded gaskets, the air inside the profile can act as a buffer to that overfilling. Although there are standard designs that are most commonly used, gaskets can be optimized for every system based on the unique situation, such as the tolerance stack up, the out of flatness, the large gaps that are necessary to seal, and many of those can be handled with hollow profiles. Here is an example where a D profile leaves areas of low sealing load marked on this picture with red arrows. One option to mitigate this challenge is to increase the number of fasteners, but another and more preferred option is to design a different profile, such as an omega profile, which does not have the same reasons of low sealing load or liftoff. Also, such engineered cross sections can handle higher tolerance and out of flat conditions than traditional molded gaskets can. Such gaskets can all be applied to various flange types, such as stamped steel, die-cast aluminum, plastic, and each cross-section profile can be optimized for the specific flange type and the other design parameters, such as flatness, stiffness, flange bending, etc. And finally, also I'll mention that these gaskets can be designed with different types of attachment options, depending on the specific flanges and the geometry design. Next, a brief overview of material options. Almost all of the material families can be offered in extruded gaskets. Although for battery perimeter sealing, because of the environment, EPDM and silicone are most commonly used. The other joints in the EV applications can use other materials depending on the fluid and the temperatures that they're exposed to. To ensure that the material used can meet the functional and the durability expectations, There are several accelerated material tests that are performed. One test, which is most representative of the sealing applications, is uh, measuring the compression stress relaxation. In this test, a specimen is compressed to a certain level and then aged in an accelerated environment. As the material relaxes over time, the sealing force decreases, and this test measures that decay in the sealing force and is a good indicator of how well and how long term the gasket will function. Through validation, there are certain parameters that have been established to indicate good service life performance, such as what we saw here is a minimum of 10% retained force after 3,000 hours of simulated aging. Now, not all materials, even within the same family, behave the same. The performance is very dependent on the formulation of the compounds and how the material is processed. The two charts here represent the performance of two different Parker materials, one in the EPDM family and the other in the silicon family. And both exhibit very high retained forces even after 3,000 hours of aging in the simulated environment for EV applications. And another required characteristic of sealing materials specifically for EV is flammability. And there are industry standard tests and ratings used. Most commonly, UL 94 rating is used. V0 is the least flammable rating for elastomer materials. And Parker has materials in the two most common material families of EPDM and silicon in both the V0 and the HB ratings, which are most commonly called for sealing EV applications. Since we are discussing extruded and spliced gaskets, it's also important to speak about the spliced joint. Typically, the spliced joint is the weakest point in a gasket. Although different splice joints would appear the same visually, it is the strength of the splice joint that matters. So the chemistry of the splicing material as well as the process used differentiates one splice joint from the other. And Parker has over the years made several technological improvements to increase the splice joint strength. As you can see in this in the data tables, 30 to 40% increase in splice strength has been obtained, primarily through the application of the right chemistry development and the processes. How do we make sure that the gaskets will meet the service life expectation? There are specific functional tests that have been developed to simulate EV applications by simulating various thermal and environmental cycles. These types of design validation tests are primarily meant to increase confidence in the design. With all that, one of the more significant challenges in battery pack seals is the installation, because these gaskets are very large and very flexible and thus more difficult to handle. Installations can be time consuming, expensive, and if wrongly installed, these gaskets can cause leakage and early failures. So working with the assemblers, there are different ways to mitigate the assembly risks. Examples are proper use of fixtures, locators, as well as mechanized assembly where applicable. So finally, to summarize it all, this table qualitatively represents the benefits and the shortcomings of the various technologies used for sealing battery perimeter seals. Extruded technology, as the one we talked about, fares well compared to some of the other gasket technologies, particularly in handling greater tolerances, lower installation loads, lower sealing loads, the potential to reduce number of fasteners, and overall serviceability and system cost. Additionally, it also avoids installation of more costly equipment at the assembly location for specific technologies like the form-in-place gasket and the RTV. So with that, I will hand over to Will for the closing comments.
Thank you, Bwani. So just to summarize, extruded gasket technology for battery perimeter seals offer many, many benefits, deal with many other things that are challenges with other technologies, provide low closure force, make a seal that's more robust to tolerance variation, more serviceable, and can be made in almost any material that you could hope for in this application. Thank you so much for listening to this presentation. There will be a recording available for participants to reference later. Parker is a company that is committed to helping electrify the transportation industry. We supply seals, shielding, thermal interface materials, and structural adhesives for almost every application you can think of. As some of you may have heard, Parker recently completed our acquisition of Lord Corporation, whose broad portfolio of engineered materials will help Parker achieve even greater success in these areas. Thank you again for listening, and look for the recording of this webinar in the near future.